Yeah. Though we know who we are, yet we know not what we may be. So maybe I'm the one, or maybe I'm crazy. I'm from.
Welcome back to your No Malarkey Guide to Programming. My name is Kalu. So in this video, we're going to continue on where we last left off. The first thing I want to do is point your attention to this YouTube video. This is a wonderful YouTube video. It explains simple linear regression, the very basics. It's by this YouTuber named Brandon Foltz. He makes good content. I just recommend subscribing. I think I'm already subscribed. Oh, I wasn't. Well, there. I just subscribed. So I recommend subscribing if you aren't already and checking out his content. But watch these videos. So this is what I want you guys to focus on. We've been trying to guess this mystery NBA player. We've been trying to predict what his height is. And that's a main thing in machine learning and in the subset of artificial intelligence, or at least a specific artificial intelligence, or narrow or weak artificial intelligence, is really based on function approximation, or just prediction. Let's call it prediction for now. And that's what statistics is really good for. So when we're making a prediction with only one variable, the only variable we have is the heights of the average NBA player. So whenever we're making a prediction with only one variable, then the best way we can do that is just the mean of the dependent variable. So you can imagine here that the height of the NBA player, we're trying to guess this mystery player's height, is dependent on a few factors. One of those factors could be just like the average height of a male, we could assume, or it could be dependent on the average height of an NBA player, or we can make it dependent on another factor, like maybe the weight. Usually the heavier you are, the taller you are. There's usually some correlation. It's not always the case, but there's some association where there's some positive correlation where the more you weigh, or the taller you are, let's say that, the more you weigh. We can agree to that. So in here, if we're trying to predict his height, the dependent variable is the height, and the independent variable, we can have a whole bunch of them, and we can just represent that. We can just only now focus on one independent variable, and we can say that's the NBA player's weight. So using the weight, we can try to predict the height. That sounds good, right? That sounds good. If you have any questions, just read this thing right here. Reread this. So I'm gonna open up my terminal, and we're gonna refire just so we get used to the process of doing this. I'm gonna close this terminal actually, and then open up another terminal. And as we're used to doing, we're gonna go ahead and CD to our desktop. As soon as it loads, CD to our desktop, then CD into linear regression folder, and then open that, activate your virtual environment. Now I want us to go into, remember, if we do ls here, we have this NBA_ACN_WT.CSV file. So we're gonna enter Python, import our dependencies, import pandas as PD, import matplotlib as, or .pyplot as PLT. We haven't used this PD yet. Oh, I'm sorry, we have used this PD. What we haven't used is NumPy, but we will use it probably in this video. I keep promising that, but we haven't used it yet. Maybe in this video we'll use it. So we've got our imports, and as you remember, we just want to pull in that data. We want to read that data. So let's call it data, and that data is from this file right here. So to do that, we can just use pandas. They have this function or this method called read CSV, and it takes as an argument the path. So underscore, let's go ahead and write this path right here, CSV, and it should read that. And remember, we're going to get this error code, which we can fix by saying can't decode Unicode right here. So I'm just going to go back to this page, and I want to get that encoding. It's going to fix this. I guess I can remember this, ISO 88591. So let's run this again and give it an encoding. Encoding equals ISO 88591, and just make sure that that is the same. ISO 88591. That looks good, and we're going to press enter, and there it is. It works now that we gave it this encoding. So we can press data and print out our data, but really we just want the heights. So let's get heights equals data, and height, And we know to call it this because we can look at the head of data.head, and we see that it has 1, 2, 3, 4 columns, and the names of the columns are player, position, weight, height, weight, age. We just want the height right now, so we can use this name. I'm going to copy it right there. I'm not going to copy it. I'm just going to write. So we want heights equals data, and here we write the same name as here. If we wanted weight, if we wanted this column, we would write weight. Data equals alright, so we have all the heights. Perfect. And we learned that the average of the heights is 79. So if we just had to do a dumb guess, we would just guess our NBA player is 79. We were able to figure out that maybe this isn't the best approach. And 79 is in inches. Remember that this is height is in inches, and that's about 6 foot 5 inches. But so this isn't the best estimate. And by the way, in the last video, I was saying estimate for is a noun. I apologize. I watched the video. I was like, no. So this isn't the best estimate, but we can do better. We can figure out, one, how bad this estimate is, and to figure that out, that's something called the square of, oh gosh, what is it? What is the name? The square of sums error. Oh gosh, I can't believe I'm forgetting the name. Square of sums. So sad. So sad. This is why I should have. So this video actually, sum of squared errors.
Which is another way of saying.
So right here. And please watch this video. It's very helpful. It teaches you the sum of squared errors. And that really, if we remember the way we plotted the line last time, we used this PLT to plot this line. We did heights and give this dot right here. And then we can also do PLT dot horizontal line, and we want to plot this mean, this 79.06. So let me just write heights dot mean, and then PLT dot show, and here it is. So here's our mean, and this person has a whole bunch of data points. Here's a data point, 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 and we have 500 data point. Here's a data point, here's another data one, here's another. Actually, here's 2 data points. So we have a whole bunch of data points. Player number 1, player number 505, and 505 is Hashim to beat, and player number 1 is Nate Robinson, I'm pretty sure. So we have a whole bunch of data set, and this is the average height right here. And we can figure out that all of these players under this height are shorter than the average, and all these players above this line are taller than the average. And this is the same thing that he did, but we want to figure out what's called the sum of squared errors. And this is going to help us figure out how good is this model. Our model is just a means of prediction, the method that we use to predict. And the model we chose to do is only use one variable, the average heights of NBA players, and then get that mean, the average, and guess that the mystery player could be somewhere around that height. So to figure out, we really want to compare our models by comparing the sum of standard errors. So we can get a sum of standard errors for different models, and then we want to minimize that, make it as low as possible. What does all this mean? Again, we follow a bottom-up, not a top-down process of learning new disciplines in the Kulu method of learning new disciplines. We always do inductive reasoning and not deductive reasoning. We learn by example, not by necessarily understanding every piece, every rule, every step of the process. We listen to the whole sentence first before we ask, what does this mean? And we don't interrupt at just the first 2 words. So just listen to the whole video, and then if you still don't understand, watch it again and maybe try to look at some supplemental resources to get a better intuitive understanding. Or do more tutorials, really. That's what I would suggest. So with that being said, let's try to figure out what the sum of standard of square errors is. To figure this, we just want to calculate the difference between our guess of the NBA player and the actual NBA player. So our guess is just the average. If we had a guess of mystery NBA players, well, we have a whole data set of real NBA players. Let me close this and again show our data set. So data, we have a data set of real NBA players. So instead of guessing, right, I just want to say our guess is 79 inches. Well, let's see for every player how wrong our guess was. So for Nate Robinson, his height is 69 inches. So if I did 69 minus 79, which was the average, and just to be more precise, I'm going to do heights.mean, then I'm going to get -10. Is that right? Was it 69? That was more than I thought it was. It was a lot more than I thought it was. So anyways, the difference between the average NBA player and Nate Robinson is 10 inches. That's a big difference. Wow, I did not know. That's a big difference. So it's 10 inches. Now, we don't want just this because it could be a negative number. We want to square it. So just multiply that by itself. So let's say difference. Let's do this again and say difference equals. And then we want to get difference. So now we have difference. It should be 10 inches. But we want difference times difference. Difference times difference. ENCE. And that is 101. That is a really lot more than I thought it was. Wow. So this is what we want. But we don't want this for only Nate Robinson. We want this for every player. So we want to get this for every player. So let's do Nate sum of sum of squared errors equals difference. So Nate sum of squared errors equals difference. So this Nate sum of squared errors, I still spelled it wrong. Let's do it a third time. Okay, so this Nate sum of squared errors is sum of squared errors is difference times difference is 101. Now we want to get it for every single player. So let's get it for Isaiah Thomas. Now his is going to be the exact same as Nate's because they have the same height. So let's say Isaiah. How do you spell Isaiah Thomas? ISAIAH. And his equals the same as Nate's. So now we have two players. We want to do this for the third player. Let's do it for the third player. Let's do it for Hashim Thabit. So let's do his is 87. He's 87 inches. That's quite tall. So our guess was so 87 minus our guess. Let's figure out heights.mean. Our guess was 79. So the difference between what our guess would be for a random mystery player is 79 inches, the average player of an NBA player. But what Hashim is 87. So we were 7 inches away. The 7 inches is the difference between Hashim Thabit and the average NBA player. So we want to square this again. So we want to do times 87 minus heights.mean. That is not right. I think there are some order of operations issues right there. So let's just do diff equals that, and then diff equals diff times diff, and then diff equals this, and let's call this, how do we say his name? Hashim sum of squared errors equals diff. So now we have all these sum of squared errors, but we want to get the rest of the 501 players. We only have 3, and we're not going to do this for every single player. You guys at home are probably annoyed that I did this for these 3 players. So we need to do some action to do this to every single player all at once. So why don't we first get the difference between the heights? So let's get difference between the average in the actual height of every NBA player. So what we did was the average, let's just call it mean equals heights.mean. So mean is 79, and so mean minus every single player for Nate Robinson, it was 69. So we want to do this for every single player. So to do that, we can say diff equals this loop, and we're gonna do mean minus h for h in, or say mean minus heights for height in heights with an s at the end. And then we're gonna write diffs, and there it is. We have let's see how many numbers are in here. So there's 505 numbers, great. But we don't want just this, we want the squared, right? We want it squared with itself. So in order to do that, we're gonna write diff equals, and then let's say diff squared equals, and we could say diff times diff for let's say difference, let's say num times num for num in diff, and we'll write this, and then diff squared is now all these numbers but just squared with themselves, and that looks good. And we can see the last number in diff squared is 62, and then the last number in diff was 7.9, and we can see 7.9 times 7.9 is indeed 62. So this looks like it works. This is looking great. Now we want the sum of this number, so to do that, let's just do sum diff squared, and that gives us our total sum of squared errors. Why is this important? We're going to compare this sum of squared errors for our model using just the mean with a different model, which we're going to use two variables. We're going to include the variable heights. And should we do this in this next video, or should I keep you guys waiting for in order to actually use NumPy? I'm going to keep you guys waiting, keep the suspense. So in this video, all we did was figure out this sum of squared differences, sum of squared errors. And this isn't going to be, you're not going to understand why this is important until we get to the next video. So if you waited patiently until the end of this video to understand what we were doing in the context, I apologize. One more video and then you'll really understand that. But right now, you want to always do this. So if you look at his video, he said around minute number 20, that simple linear regression is really a comparison of two models, one in where the independent variable does not exist. So remember here, our dependent variable is heights. The height of our mystery NBA player depends on some factors, right? And then, so our independent variable, we don't know those factors, so we're just going to use the average height, right? What we're trying to guess. So one in which the independent variable does not exist, and the other uses the best fit regression line. Pay attention to this. That's what we're going to do in the next video. We're going to use the best fit regression line. But the model we're doing right here is one where the independent variable does not exist, and whenever there's only one variable, the best prediction for other values is just the mean of the dependent variables, and that's what we did right there. So I hope this math talk makes sense to you. If it doesn't, don't worry too much. We're just going to keep doing by example, and the more times we iterate over this, the more sense it's going to make. So thank you for your patience. I'll see you in the next video. And again, keep this number in mind. This is so let me call this our SSE equals sum diff squared. And we're going to remember this number, SSE. And that is the SSE for our first model where we only have one variable. All right, see you guys at the next video.
Financial freedom, my only hope.